Welcome to Module 15 of two-dimensional dynamics. Today's learning outcome is to solve for the velocities of a planar rigid body in motion using the relative velocity equation that we developed in the previous modules. So here's a picture of what we developed before. We have a generic body, 2 points on the body, and the relative velocity equation relates the linear velocity of those 2 points on the body to the angular velocity of the body, the motion of the body, and its geometry. So here's a worksheet of an actual problem. This is the piston cylinder mechanism that I used as a demo before, and this problem is just a mirror image of this piston cylinder. I have a crank arm here, which is body B1, which just is a portion of my wheel, but it's the same body. It's got a fixed point at O, so it's rotating about a fixed axis. I've got a connector arm here, B2, connected to a piston that's undergoing linear translation. And I know in the problem that the crank arm has an angular velocity of 10 radians per second clockwise, but in my model here, since it's a mirror image, it's counterclockwise. And we want to find at this given instant what the velocity is, the linear velocity is of the piston itself. Okay, so let's go ahead and talk about a strategy on how to solve this problem. Generally, I would think the best approach is to pick a body, one of the bodies in the problem, and go from knowns to unknowns. So in this case, the body I know something about is body B1, the crank arm. I know that it has a 10 radian per second clockwise angular velocity, and I also know that its velocity at point O, since it's a fixed pin, is 0. So let's go between O and A and write our relative velocity equation. So I have velocity at A, which is unknown, is equal to the velocity at O plus theta dot from O to A in the K direction crossed with R from O to A. And so in this case, I know that the velocity of O is 0. I'm given that theta dot, or the angular velocity of the crank arm B1, is 10 radians per second clockwise. And so if I go 10 radians per second clockwise by the right-hand rule, that is into the board or in the minus k direction. So I've got plus minus 10k crossed with R from O to A, and going, the position vector in going from O to A is minus 3 in the I direction and plus 4 in the j direction. So that's going to be minus 3I plus 4j. And so the velocity of A then is equal to k cross j is minus I, but I got minus 40 times minus I, so that's plus 40I. And then k cross I is j. Minus 3 times minus 10 is plus 30, so we get plus 30j inches per second. Okay, so I now know the velocity of this point on body B1, the angular velocity of body B1, and the linear velocity of point A. I want to keep going toward the unknown that I want to solve for, which is the velocity of pin B. And so let's continue on. And so here's my result so far. Now I'm going to go from what is now known as the velocity of A to velocity B using the body B2. And so now I have the velocity of B is equal to the velocity of A plus theta dot AB in the K direction crossed with R from A to B. And that's just an application of the relative velocity equation. We know what A is. We don't know what VB is. We don't know what theta dot AB is. We can find RAB from the geometry. Do we know anything? We want to reduce as much as possible the number of unknowns as we can. So do we know anything special about the velocity of point B that will allow us to reduce some of the unknowns? And what you should have thought about and discussed, or thought about and arrived at, was the velocity of B is in the I direction only. So the only unknown for the velocity of B is the magnitude, not the direction. So I can then write the velocity of B in the I direction is equal to the velocity of A, which we found to be 40I plus 30J, plus theta dot AB in the K direction, the angular velocity of body B2, crossed with R from A to B. We're going to have to use a little geometry here. And so I know by Pythagoras' theorem, rise is 4, the hypotenuse is 13, so this distance is 12. And so I'm going to go, and going from A to B, I'm going to go 12.4 in the I direction and down 4. So we're going to have crossed with 12.4 I minus 4J. Okay, so let's continue on again. Here's the result that I have. So I've got, let's do the cross products out here. We've got VBI equals 40I plus 30J. And then I've got K cross I is J, so I'm going to get plus 12.4 theta dot ABJ. And then K cross J is minus I, but I've got minus I times minus 4 times theta dot AB, or plus 4 theta dot ABI. And now I'd like to you to think about, what do I do next? How can I finish up the problem? I want to find, I know the direction of the velocity of B. I need to find the magnitude of it. And what you should arrive at is that you should use match components like we have in past courses and past modules. So I'm going to match the J components to start on both sides of the equation. And on the left-hand side of the equation, I don't have any J components, so that's 0. Equals, on the right-hand side, I've got 30 plus 12.4 times theta dot AB. And what that allows us to arrive at is that theta dot AB, if I solve for it, equals minus 2.42, or theta dot AB, the angular velocity of bar B2 as a vector, is minus 2.42 K radians per second. And so what that means is this bar B2 here is turning with an angular velocity of 2.42 K radians per second. Since it's negative K, it's a clockwise rotation. Finally, we need to solve for the velocity of B. How do I do that? The magnitude of the velocity of B. And what you should say is match the I components. And when I do that, on the left-hand side, I have VB. On the right-hand side, I've got 40 plus JI component 4 times theta dot AB. And I know that theta dot AB, I just solved for it, is minus 2.42. So I arrive at VB equal to 30.3. That's the magnitude of VB. I know its direction. So my final answer is VB as a vector is equal to 30.3 inches per second in the I direction. And I've solved my problem. And I want to go ahead and give you a chance to solve a similar problem. So here's a worksheet for you to do on your own. I've included the solution in the module handouts, and I'll see you next time.